Another approach for solving the anagram problem involves counting the number of occurrences of each character in the first string and ensuring that the counts are the same in the second string. So I'm going to add a new method here, public static boolean r anagram 2. We need the same parameters, first and second. Now here we want to iterate over the first string and count the number of times each character occurs. We can use a hash map or an integer array, which is kind of simpler. It requires less code. We talked about this in the video about finding the most occurring character in a string. So if you skip that video, make sure to go back and watch it. So here we declare an integer array called frequencies and set it to a new int of, now here we can pass 256 as the number of ASCII characters, but let's make this more interesting. Let's say the input only contains the letters in the English language. We have 26 letters in English, so we pass 26 over here. Now, as I told you before, you should avoid these magic numbers because they don't reveal their intention. So to improve the readability of this code, we declare a final integer or a constant called English alphabet. And we use all uppercase letters to name constants, okay? So we set this to 26 and use it over here. That is better. Now we iterate over our first string and count each character. So for I, set to 0. As long as it's less than first the length, we increment it. Here we should set frequencies of, we get the current character, that is first the char at I, and then increment the value. So initially all these values are 0. Every time we read a character, we increase its frequency. Now here's the tricky part. We cannot use the current character as an index value here. Because if the current character is a lowercase a, its numeric representation is 97. But our array has only a space for 26 items. So here we need to map this number to a number that fits in this array. And that's really easy to do. We add minus a. So if the current character is a lowercase a, we'll get 97 minus 97. So the index will be 0. If the current character is a lowercase b, we'll get 1. Now, what if the current character is an uppercase letter? Well, we have to convert our first string to lowercase before we do this. So we set first dot to lowercase. So we're done counting the frequencies in our first string. Now we have two options here. We can count the frequencies in the second string and then compare the two frequencies array for equality. But that's a little bit tedious. We have a better option. We can iterate over the second string. For each character, we'll reduce its frequency in our frequency array. Let me show you. So we need another loop for I set to 0. As long as it's less than second dot length, we increment I. Now, before we go further, we want to make sure that the second string is also in lowercase. Now here we go to our frequencies array. We get the current character. So second dot char at I minus a, and then decrement its value. If these frequencies are equal, the value at this index should never become 0. For example, if we have 3 a's in our first string, we should be able to decrement this value 3 times. So only after this loop, the value at this index will be 0, not inside this loop. So if we get 0, that means in the second string, we have fewer occurrences of the current character. So before we decrement this value, we check to see if frequencies of second, the char at I minus a equals 0. If so, then we return false immediately. Now we have some code duplication, so let's extract this expression into a separate variable called index and then use it in 2 places. That's better. So after this for loop, that means the counts are the same, so we return true. And just like our first implementation, we should check for null values at the top. So if first equals null or second equals null, then we're going to return false. So this is the second implementation. Now let's do time complexity analysis. We start with our first implementation. What is the time complexity of this method? Well, here we have an O of n operation. because we have to iterate over all the characters in the first string. So O of n. Now, array.sort uses the quicksort algorithm. So here we have O of n log n. We have the same story over here. And finally, comparing two arrays for equality is also an O of n operation. Earlier you learned that O of n log n is slower than O of n. You can verify it on bigocheatsheet.com. So O of n is in the yellow area, whereas O of n log n is in the orange area. So because this operation is slower, the time complexity of this method will be O of n log n. Now let's look at the time complexity of the second implementation. So here we have to iterate over our first string. That is an O of n operation. We have the same story over here. So the time complexity of this method is O of n. So the second solution is faster.